Okay, this is the definition of a segment bisector. So the point line, ray, line segment, or a plane can intersect a segment and bisect the segment if and only if it intersects the segment at the midpoint. So in this diagram, we're given that ray HK is a bisector of segment AB. That means that ray HK is going through the midpoint, which is point M, of segment AB. That's all the definition says, is that we can write that as an if-then. Remember, we wrote this as an if and only if because it's a definition. Definitions can be written as biconditionals. That means that the if-then statement that we could write and its converse are true. So the if-then statement would just say, if a point or line or ray or segment is a segment bisector, then it intersects the segment at its midpoint. So I could say that point M in this diagram is a segment bisector of AB. I could say that segment HK is a segment bisector of segment AB. That means that it takes segment AB and it finds the midpoint of that segment. We could also just say that this ray, HK, starting at H going all the way through K, is a segment bisector of segment AB. Now that's all the definition tells us, but we know what a midpoint is. And so we could keep going a little bit. First, let's just say also on this that the converse is true. Trying to figure out what letter I wanted to write there. Converse is also true. That means if I know a segment or a ray like HK, if I know ray HK goes through the midpoint of segment AB, then I know that that ray qualifies as a segment bisector. If I know that it's a bisector, I know it goes through a midpoint. If we know that it's a midpoint, then what? Well, then we know that it splits the segment into two congruent parts. So we're going to use a segment bisector and definition of midpoint to do problems. That's what this looks like. Line L bisects the segment. Find the indicated length. So line L bisects the segment. That tells me E is a midpoint. Because E is a midpoint, I know that DE is congruent to EF. So it says find DF if DE equals 17. So if DE equals 17, then EF has to equal 17, and DF is going to equal 17 plus 17, which is 34 centimeters. Likewise, line L bisects segment AC. So because line L bisects the segment, we can tell from the diagram that it goes through B. So point B is the midpoint of the segment. Because point B is the midpoint of the segment, then segment AB and segment BC are congruent. And so if AB equals 6, then segment BC has to equal 6. So AC has to equal 6 plus 6, which is 12 centimeters. Sorry, I'm going to go back to this one for a second. So with the midpoint definition, we set the two sides equal and solve for x. We can do the same thing if we know that there's a segment bisector, because the segment bisector goes through a midpoint, so then we can do the same things with midpoint. Just to make sure we're clear on the two parts though, we have definition of segment bisector, which we just looked at. I kind of wrote these as an if and only if symbolically. So instead of putting if and only if in the middle, I have an arrow going both directions. So if something is a segment bisector, then it goes through the midpoint. Converse, if something is a midpoint, then if something is a midpoint, then it is a segment bisector. Likewise, if something is a midpoint, then we have congruent segments. or if we have two congruent segments that are being split up from one big segment, then we have a midpoint. So, question then, what can we conclude using the law of syllogism, right? So we have if segment bisector, then midpoint. We have if midpoint, then congruent segments. So law of syllogism would say if a point is a segment bisector, then we have congruent segments. So that's true logically. Nothing wrong with that. We used the law of syllogism in our proofs last unit by following that train of logic, but we listed out every step. So we have to do that with our proofs in this unit as well. So if we're using definition of segment bisector, it's going to tell us midpoint. And if we're using midpoint, it's going to tell us congruent segments. And this is very similar. You'll see this in proofs very similar to what you did last unit with if something is large, then it's not small. You had to say both. You got points off on your test if you didn't go from large to not small, but you needed not small. Or if you didn't go from small to not large and you needed not large. So you'll see that in the next couple of proofs. But that's the definition of segment bisector.